Semiconductor devices, important model again. A light emitting diode using gallium arsenide material with band gap 1.42 electron volts. The wavelength of the light emitted from this LED, light emitting diode is. So, energy is given here. If energy is in electron volts, okay, we are having two different formulae. 12,400 by lambda in angstrom. This you will get in electron volts. Otherwise, second formula is, if it is in nanometer, you see, answers are in nanometer. So, directly we can go with this formula. So, energy and this lambda is in nanometer. And you will get this energy in electron volts directly. If lambda is in angstrom, 12,400. But if it is, because answers are in nanometer, we can go with nanometer. So, 1240 instead of 12,400 by lambda. So, from here bring energy, this energy is given 1.42. So, bring 1.42 here and lambda this side. Lambda is 1240 by 1.42. If we calculate, we will get nearer to 875 nanometer. Actually, it is around 873.6. But we are taking this approximate word here. So, 875 nanometer. Okay, Nana. Next one. Next, a Zener diode. Okay, Zener diode is given with breakdown voltage 10, means there. Is used a voltage regulator, current through Zener diode, means this one. This is how much? Current through Zener diode. So, here, Nana, this entire circuit can be redrawn like this for convenience. This is series resistance. Now, this is input. Okay, this circuit can be imagined like this. We are giving input, that input is 20 volts. And a Zener breakdown voltage, this is given, let it be V2, 10. Input is 20 volt. And these two are parallel. In parallel, voltage is same. So, this output is also, if it is 10, the output voltage is also 10. So, input 20 in that, 10 volts is taken by Zener diode. This is series resistance. So, out of 20, 10 is taken by Zener diode. 20 minus 10, the 10 will appear here. So, this is V1, 10 volts. Now, here current flows. A total current I flows into the circuit, means here. And at this junction, say A, this current splits as current through Zener diode and as current through load resistor. This one. This is calling, we are calling it I3, nothing but load current. This is Zener current. I2 is IZ. So, let us apply for the output, Nana. For output, Ohm's law, V output, load current into load current. So, load resistor 500 into load current. This output voltage is 10. So, load current is 1 by 50. So, load current is 1 by 50, this one. So, this I3 is called a load current, 1 by 50. So, this is Ohm's law at load resistor. Now, again we are applying Ohm's law here means at this point. So V1 is equal to current I into this series resistance. Series resistance 200. This is 200. So into 200. This V1 is 10. This is total current 200. So total current is 1 by 20 ampere. Now at the junction, this is junction RAM. At the junction, this current is splitting as I1 is splitting as I2 and I3. So at the junction, I splits as I2 and I3. Now our total current is 1 by 20. And I2 is Zener current, that only we are finding. I3 means here according to load current, we got 1 by 50. So I want I2, bring 50 this side. So 1 by 20 minus 1 by 50. So 1 by 20 minus 1 by 50, after calculation 3 by 100 or 30 milliampere. This is Zener current. This is Zener current. Okay, Nana. Very, very important model. You can expect one problem on this, on Zener diode. We are applying 2 times Ohm's law. Ohm's law at load resistor, Ohm's law at series resistance. Next. Here, 2 diodes are connected in the same circuit with the battery. This is positive and this is negative. So current flows like this. This is positive connected to P side, forward bias, positive, forward bias. So both the diodes are working. Germanium junction voltage 0.3 volts, silicon 0.7 volts. So now here battery potential 15 and here we have to overcome junction potential 0.3. We are spending 0.3. At silicon we are spending 0.7. So 15 minus 0.3 minus 0.7, 15 minus 1, 14. So here 15 minus 0.7 minus 0.3. And the total resistance 1.5, 2.5 in series. These two are in series. So you will get 2.5 plus 1.5, 4. So 15 minus 1, 14. By 2.5 plus 1.5, 4. Now, this is 7 times, this is 2 times. This is current. But is asking voltage across load resistance. He is calling this a load resistance. So, voltage across load resistor, current into load resistor, current 7 by 2. Current through this into load resistor 2.5 kilo. So this is equal to now 3.5 multiplied by 2.5 and here this is 2.5 plus 1.5 kilo. So kilo becomes milli. So here also milliampere. So milli and kilo cancel. So no kilo here. (3.5) multiplied by 2.5. This is voltage at the resistor, and if we calculate, Nana, it will be around 8.75. 3.5 multiplied by 2.5. Very, very important model when 2 diodes are given simultaneously. Next one. Nana, here. assertion. Diffusion current in a PN junction is greater than the drift current in the magnitude if junction is forward biased. So in forward bias, this is P side, the N side. In the forward bias, electrons. In the forward bias, holes diffuse from P to N side and electron diffuse from N to P side. So diffusion of majority charge carriers takes place through the junction in forward bias. So diffusion current in a PN junction is greater than the drift current. So in forward bias, current is mainly because of majority charge carriers. Automatically drift current will be more. Next reason, diffusion current in a PN junction is from N side to P side. But observe carefully here, whole direction is taken as current direction. Whole direction is from P to N side. And that is why here assertion is correct. Reason is not correct because diffusion current is from P to N side. Next. The current I in the network is, observe carefully, battery positive, negative. Positive this side, it is positive. This is negative. Positive given to N side, reverse bias. This diode, it will not work. And here, negative given to P side of diode, this will not work. Then whatever current we are giving, that current will pass through. That current given by battery travels like this. It will enter into this. Because it is not working, it will go upside here, into this. And again it will come like this. Finally into this. So this 5 ohm and this 20 not working. This 10, 5, 10 series. 10 plus 5 plus 10 series. This is 25. 25 and in this circuit also 5 is there. Plus 5. So R effective is 30. 25 plus 5. Now current is equal to EMF by R effective. So I is equal to 3 3s, 3 10s. So current is equal to 0.3 ampere. This type of model definitely can expect in NEET exam. Very, very important. Okay, based on diode forward bias and reverse bias. So 0.3 ampere. Next. What is the conductivity? Is asking conductivity, sigma, of a semiconductor sample having electron concentration, hole concentration, electron mobility and hole mobility. This is one peculiar model similar to current electricity. So conductivity in a semiconductor, Ne mu, this is for electrons, plus N times E mu, this is for holes. So in semiconductors, conductivity is due to both electrons and holes. So here sigma is E common. This is concentration or number density of electrons, mobility of electron, plus here E common, number density of holes, mobility of holes. This is conductivity. So here sigma is equal to charge of electron, number density of electron, mobility of electron, number density of holes and mobility of holes. So this is 1.6 into 10 power minus 19 charge. This is 5 into 10 power 18 and its corresponding mobility 2 into 2 plus for a whole concentration 5 into 10 power 19 and mobility 0.01. Now here this is 2 into 5 10, 10 power 18 into 10, this is 10 power 19. Here 10 power 19 is there, common I took. So here 1 plus, I took this as common, 0.05 remaining. Outside, of course, we are having this value 1.6 into 10 power minus 19. Plus 19 minus 19 cancel. So 1.6 multiplied by 1.05. This, if we multiply, we will get 1.68 ohm meter inverse. Very, very important for NEET exam. This conductivity, very, very important. Okay, Nana. Next. Nana, two statements given here. A pure semiconductor has negative temperature coefficient, alpha negative. Alpha negative means as temperature increases, resistance decreases. Yes, correct. Semiconductor is non-ohmic. Next, on raising temperature, more charge carriers are released into conduction band. This is also correct. So as they gain energy, they jump into conduction band. So both are correct, Nana. Statement 1 is true. Second one is also true. Statement 2 supports first one. Okay. Next. Nana, here. In a PN junction, this is very, very important model. And is giving here. This is input actually given into this circuit with one diode. A single diode acts as a half wave rectifier. So when positive half is given, diode positive forward bias, it works. So in the forward bias it works, and this 5 volts is accepted, and you will get output here. So in the forward bias, this is accepted. In reverse bias, -5, diode will be in reverse bias, it will not work. So this negative value will not get in the output. It is a half wave rectifier. So here this is correct. So current will flow only in forward bias. Next, Nana. Which of the following gives a reversible operation? This is actually a new type of model which I am selecting. This diagram you treat like this. Nana, this one is like this. Actually, it is like this. This is a single input. Nana, single input NAND gate. Single input NAND gate acts as a NOT gate. This one acts as a NOT gate. So this NOT gate has this reversible operation. Wantedly I selected this new type. Okay, a logic gate is reversible if we recover input data from output. Hence, it must be a NOT gate. This is NOT gate. Okay, Nana. Next. In the circuit, this given, this bit is given many times in the exam. Just you have to identify which gate it is. So here, A and B are two inputs, P side, N side of first diode, P side, N side of second diode. And resistor is connected to earth. This is output. Now, let us give here, input A is equal to 1. 1 means here high value. B, let us give 0. Means a low input. When A is 1, high voltage is given. High voltage means P is high, forward bias. This is forward bias. Here 0 is given, low voltage. If it is low voltage, P side low voltage, this is reverse bias. This will not work. Current flows like this. Like this. And for the current, there is one path here and another path here. In this path, there is a resistance. In this path, no resistance. So, current flows like this and you will get output. So, A1, B0, still I am getting output. This output here is called as C. So, I am getting output 1. 1, 0, but still I am getting 1. So, it acts as OR gate. So, he is asking just identify what type of gate it is. 4 marks will be in your pocket. Okay, Nana. Next.